Okay, folks. So today I want to continue what we were discussing in my last video, which was calculus, specifically first derivatives, and how in today's class this applies to slopes of tangents to curves. This is a big part of what we're doing when we do calculus. As I said before, calculus is about rates of change, and mathematically, how we generally measure rate of change is through the slope of a line. Slope being a measure of the steepness of a line. So, first of all, what is a tangent? Well, the definition of a tangent here, a tangent is a line which touches a curve at only one point of intersection. Okay? So, touches a curve at only one point. Now, these curves can be curves of a quadratic equation with its tangent here, or the curve of a circle with its tangent here. The important thing isn't the type of curve, the important thing is that the line touches it at only one point of intersection. So a line that would cut through a circle here and here, or through my curve here and here, these are not tangents because they cut at 2 points of intersection. A tangent only touches the curve at exactly one point of intersection. So when we differentiate the equation of a curve, such as a quadratic equation, then we get an expression that we can use to find the slope of any tangent to that curve. To get the slope, we just sub in the x value for the tangent we wish to find into our first derivative. Now, first derivative, I think, is a new term, but we are going to discuss it in a minute, okay? If we take a look at an example here, the function y equals x squared. This chevron symbol here, folks, is how we type or represent that we're taught that it's a power. So if you see x chevron 2, this is saying, okay, that should be x to the power of 2. On Google Slides, I had no way of inserting a maths equation to type it properly. So you'll see this symbol throughout. It just means power, okay? When we derive this, we get an expression. I'm using my f-x notation, 2x. Now, if we look back at the previous video, how do we do that? Well, if I have y equals x squared, the power comes to the front to multiply, and we subtract 1 from our power. So 2 minus 1 is 1. So this now is 2 times x to the power of 1, or just 2x. So this is our first derivative, that term I just used a moment ago. When we get our dy dx or f-x, our derivative of our function, the answer we get, that general expression, is a first derivative. So this is, now because this is a function of an equation of a curve, which I have demonstrated here, we can't get the slope of this curve. A slope is a measure of the steepness of a line. But a curve's steepness is constantly changing. As I travel along my curve, the steepness of this curve constantly changes, decreasing to a flat line here and then changing again to an increasing negative value here, okay? So it's impossible to get the slope of a curve because, as I say, the slope of a curve constantly changes as the values of x for the curve change. In other words, as I'm going from left to right. However, we can get the slope of a tangent to a curve at a specific value. Remember I said tangents to a curve are at a specific point. So when we derive a function, the expression we get will allow us to find the slope of a tangent to a curve at any value of x we sub in. And that's what our first derivative is. It is a general expression for the slope of the tangent to the curve. So going back to my example, y equals x squared, when we derive it, our first derivative is 2x. This is actually an equation for a slope. Not any slope, but rather the slopes of the function y equals 2x squared. So now, subbing in, so say I want to get the slope of the tangent at x equals 2, I'd sub in 2 for x here, so we'd have 2 times 2 equals 4. Therefore, the slope of the tangent to the curve y equals x squared at the point x equals 2 is 4. And we can see that demonstrated here, okay? I have my function y equals x squared. I have a tangent going through the point x equals 2, and this is an equation for the line. Now, I don't know why GeoGebra did this, really dumb. It has y to the times a half, but if I multiplied this whole thing by 2 to get rid of this fraction, I'd have minus 4x plus y equals minus 4.02, okay? And if we remember our coordinate geometry of the line and the equation of the line formula, y equals mx plus c, well, if I have minus 4x equals plus y equals 4, or sorry, minus 4, we bring the minus 4x across the other side, it becomes plus 4x, will be y equals 4x. And the equation of the line, y equals mx plus c, the number in front of your x is your slope, which, oh look, we found using calculus, it is 4. Okay? So, in my first video, I said calculus deals with rates of change. By finding the slope of a tangent to a curve at a given point of x, we are actually finding the mathematical value for the rate of change of the curve at that value of x. In other words, that's what slopes are, folks, okay? A slope is the mathematical representation of a rate of change. Because the slopes of a curve are constantly changing, you can't get an overall expression for the rate of change of a curve, but you can get an expression for the rate of change of the curve at a specific point or value of x. So if my quadratic actually represented something in the real world, say the path of a projectile, a rocket, or a satellite going to space, or maybe a production of a factory, well, at a specific value of x, I'm going to know what the rate of change is. In the case of my rocket, I know is the rocket accelerating or decelerating. In the case of production output, is my production still making profit or loss? Perhaps. Depends on what the equation means. But this is the whole point, is these values of x, these slope values of tangents at x, they mean real things. So let's look at a further example. Okay, we have y equals 2x squared plus 3x, and we're asked to find the first derivative. I'm now using my dy dx notation, and I'll be constantly doing this so you can get used to the two sets of notation that we have here, okay? So dy dx is equal to 2 times 2x plus 3. How did I get that? Bring down the power, multiply the term by the power, subtract 1 from the power. So the 2x of the 2x squared bit is now being multiplied by the 2 from the power, and it's 2x not squared. 2 minus 1 is 1, so 2x to the power of 1 is just 2x. So we have 2 times 2x is 4x plus 3. So this expression, also known as the first derivative of this function, y equals 2x squared plus 3x, can be used to find the slope of any tangent to the curve y equals 2x squared plus 3x for any value of x. So to find the slope of a tangent to the curve at x equals 3, we sub 3 into our first derivative. So wherever we had an x here, we're subbing in 3. So we get 4 times 3 plus 3, 12 plus 3 equals 15. If we look at my next example here, we see it again. There is y equals 2x squared plus 3. There is the tangent at the point 3. GG, we did the same dumb thing again. I don't know why. Writing this as a half, double the whole thing. And oh, look, there's 7.5 times 2 is 15, which is the tangent. So there we go, folks. I hope this makes a bit of sense to you. I've got two sets of questions. It will only take you about less than 10 minutes to do. Just to practice this, I'll be sharing this Google slide as well on our Google Classroom. If you have any questions, email me. I hope you are all doing well. I hope you are helping your guardians at home, and I hope you're all remembering to wash your hands. Okay, thanks.